everything you need for this coming set of homeworks and the online test. And just in case you missed it, Monday is a holiday. So everything has been extended now to midnight Monday. So that's when you can do your test and also in your homework. None of the tests are online yet. I haven't got around to doing them. Once this class is finished, I'll start with my first one. So you'll probably have it online, I don't know, 2 p.m. probably, or thereabouts. If you really want to get it done early, you could do it then. But as I say, you've got until Monday, so there's no big rush. So time is important, so let's work on our next section. And we're going to calculate what is called a surface integral. And you'll know it's a surface integral because it has DS's. In fact, there have been a couple of questions that we've had in the past called DS's. We just haven't mentioned the fact that they're surface integrals because it doesn't matter. But I want you to imagine that you've got a surface, this green area here, and this surface will be described, excuse me. No. 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 I did my stern voice thing, so it should last for about 30 seconds.
It's funny, I was just doing that to my dogs before class.
So, they're sucking up to me now because they know they're in trouble. Right, so pretend the last few minutes didn't happen. So what we're going to have here is a surface, and this surface is in general going to be called, if you can make it, and you need to write it this way, z equals some function of x and y. So it could be, you know, a plane, you know, 2x plus 3y plus 4z equals 10. But couldn't it be z equals x squared plus y squared, right? Or whatever it might be. But this green surface is the S that they're talking about. And you should be able to write it down as the surface z equals, and it's a function in terms of x and y. And on this green surface, there is a function, f of x, y being applied on. So if you put any of the points on this green surface, you would be able to evaluate this thing called f of x, y. Maybe each point in this surface is a different temperature. So when you're doing a surface integral, what you're adding up is the energy in the heat on that curved surface, right? Maybe each of these points on the surface could be representing a magnetic charge. Then what you're doing is summing up, right? Adding up the total electric charge. So there is reasons why you would want to find a surface integral. But how do you do them? Well, what you do is you turn this double integral, the surface integral will be a double integral, and you convert it into an equivalent double integral. And it's got various pieces to it. Do you notice that this function here, this one here, this might be called x, y, z cubed, right? It'll be a function of x, y, and z, this guy. You turn it into a function only using x's and y's, which means all the x's stay as x's, all the y's stays as y's, but see if there's any z's, replace them by what this guy here is. Right, so that's what that's saying. And when we do one, you'll get maybe a little bit better idea what I mean by that. Times a really ugly square root. This guy squared plus this guy squared plus 1. Technically, this is dz by dz squared, but that is 1. And so we're going to turn this thing into a double integral on a region D. Now, the region D, my way of describing is, can you imagine the surface is floating above the xy plane and you shone a light down? D is the shadow on the floor that you would get. So can you imagine you had a shadow on the floor, it might look like this rectangle. And this is your D. So to be able to convert this surface integral into a form that we can actually evaluate it, we need to turn this z into x's and y's. We need to multiply by this ugly square root formula. And then we can do the integral with x's and y's. And well, let's go. Here is the first one. We're being asked to do the surface integral of x squared y z ds. The plane is z equals 1 plus 2x plus 3y. So that's basically them telling me S is this plane. They have also told me then the guy that we're calling g of xy. That's this guy. And they are telling me, because it's a nice easy question, that we're only interested in the plane on this part of the world. So can you imagine they just cut a little rectangle and stuck it up? Right. So we got all the pieces. Let's see what we get. This surface integral of x squared y ds becomes this double integral over the region D, x squared y. Instead of z, we use this fella, 1 plus 2x plus 3y, times the square root of dz by dx, which in this case is 2 squared, plus dz by dy, which in this case is 3 squared, plus 1. And d is described as, these are the x's, these are the y's. The x goes from 0 to x equals 4, and the y goes from 0 to y equals 2. And it's x squared y, 1 plus 2x plus 3y. 1, 9, 10, square root of 14, dx, dy. Are you comfortable about where all the pieces of the puzzle come from, right? Why that guy there, the z, turned into that? Where the 2 squared and the 3 squared and the 1 came from, and where the limits of integration came from, right? Now, not an awful lot I want to do with this question. I'd probably pull out the square root of 14. Distribute that, you get x squared y plus 2x cubed y plus 3x squared y squared dx dy. Would you agree that's not difficult, it's just laborious, right? We're all comfortable that that double integral is doable, right? It'd be various power rules. And let's see what the answer is. And the answer according to them is what? And I will take their word for it. It's 1408 square root of 14 all over 3. Well, at least I know where the square root of 14 came from. Evidently, this fraction is what you get when you integrate that. And that is our first surface integral. So if you integrate over this surface above this rectangle on the ground, so imagine this rectangle here is these guys, and that this is the green surface. The integral of that surface using this function ends up being that value. Okay, hey, Bailey, shh, quiet. Okay. What? Yeah, what is it about workmen that they have to shout when they talk to each other, even though they're 2 feet away? There's something weird about that. Bailey, shh, quiet. Bailey, come here. Come on, Bailey, come. Come on, come. Quiet. Okay, I think we'll do one quiet between questions if we're lucky. Okay, we're going to do this surface area, which is that guy. S is the plane, 2x plus 2y plus z equals 4. And we are interested only in this surface in the first octant. So there's going to be a lot more work we can do before we are ready to set up this integral. For instance, I need to know what the surface looks like as z equals. So if you take this fella here and you want to do it as a z equals, won't you have to subtract 2x and 2y from it? So I've now got the guy we call g of xy. Now, the next part's a little bit trickier. When you do your surface, you want to know, in this case, that it's in the first octant, you want to know what does that guy's shadow look like if you drop it down as it crosses through the xy plane. So if you make this z equals 0, which is what the xy plane is, right? Do you see that the relationship you get is 2x plus 2y equals 4? So let me say it again. You want to know when this surface hits the floor, right? The xy plane. You do that by making z 0. And what you've got here, with a little bit of work, is you've got that. What that tells me is, and I'll orientate it this way, that you have got that's D. Right. If you're in the first quadrant, won't the x and the y's be positive, right? Won't the line that it makes when it hits the floor be that diagonal line? If you put that all together, can you see that you end up with a triangle? Right? Can you imagine a plane cutting the floor and then only looking at what it looked like in the first quadrant? As that plane sweeps in, do you see it would just cut that little corner there? This guy is D. So I need to set up the limits of integration for D. Well, it's going to be x's go from 0 to 2. And I'm going to do pretty much the ones we end up doing almost all the time. I'm going to do one of those vertical slice things, right? So the y value is going to go from 0 to the equation of the line. Okay, so I now know what D looks like. It looks like that guy. I know what G looks like, right? He looks like that guy. So I should be able to put all the pieces together now and set up our surface integral in a form that's going to allow us to calculate it. So we've got that guy. So it's going to be a double integral over the region D. It's going to be x times z. Well, z is this guy. Times the square root. If you differentiate z with respect to x, you get -2 and then you square it. If you do y, you get -2 and you square it, plus 1, dx dy. D is going to be x equals 0 to x equals 2, and y equals 0 to 2 take away x. If I distribute this, you get 4x, take away 8y, actually 8x and 8y, there, fix that. 4, 4 and 1, oh, 9, square root of 9 is 3, that's kind of nice. I'll stick it out there and do a dy dx. Would you agree that we've broken the back of this question? Isn't this just another horrible but relatively straightforward double integral? You comfortable with xz? You comfortable about that being 3? Are you comfortable about what this plane looks like when it hits the first octant, right? It's going to be a little diagonal triangle-y thing. And that the area D is described using these limits of integration. And according to the guy I've got here, that's 4, which I'll take the word for it. Okay, a lot to take in there. Any questions? Any piece of that puzzle that doesn't make sense? Last chance, anything? Okay, that's good news. To version of 3 then. The surface integral that we're being asked to do is just y. Well, that shouldn't be too much a problem. And the surface is z equals, oh God in Himmel, look at this, 2/3 x to the 3/2 plus y to the 3/2. And we're only going to do it in the range x is 0 to 5 and y is 0 to 2. So if they tell you that, do you know you don't need to worry about the projection? Because what they've done is they've said, look, we're only going to use this surface in this rectangle. So they're essentially telling me D when they do that, right? Which is nice. Actually, aren't they telling us who G of XY is as well? So let's put the pieces together. It's going to be the integral from x equals 0 to 5 and from y equals 0 to 2. Y is okay, so I don't need to do much with that. I'm going to have a big ugly square root. And it's going to be the derivative of this function with respect to x, and then you square it. And then the derivative of this function with respect to y, and then you're going to square it. And since it is such an ugly thing, I'm going to do it over here. Here is the surface, right? That guy. I think it's going to come out nicer if I just distribute the 2/3. So I need to know the partial derivative with respect to x. Well, multiply by the power and then reduce the power by 1. I want to know the partial derivative with respect to y. Multiply. Is that 2/3 or 3/2? Oh, shooting space. 3/2, which is even nicer, isn't it? Because all you get is that guy. Now, you multiply this by 3/2, you get that guy. Right. Okay. I know it's a lot of a mess, but if you differentiate that, you get this fella. If you differentiate that with y, you get this fella. So the derivative with respect to x was just that guy squared. And the derivative with respect to y was that guy squared plus 1. So I'm going to have the integral from 0 to 5, the integral from 0 to 2, y.
Wouldn't that be a bit, the derivative be different since you changed the numbers?
Did I change any of the numbers? Or did I just write them the way they should have been? Let's check. 2/3, 3/2, 2/3, 3/2, 2/3, 3/2, 2/3, 3/2. Multiply by the power, they cancel out. Reduce it by 1. Multiply the power, reduce it by 1. I'm not sure what you think might not be right there.
Well, you did the derivative with respect to x, wouldn't that be the square root of x?
Oh, thank you. Yes. Okay, and I can't even blame my dogs for barking, although in the back of my head, I've got a feeling that they're going to be barking any moment. This guy gets you x to -1. This guy gets you y to the -1. And this guy gets me 1. And I have a dy and a dx. Let me check. They are not negatives, they are actually positives. Okay, so I think the fact that they're now quiet has got me worried because I'm wondering what the heck they're doing. Okay. What you're going to do here is a good question. What am I going to do here? I don't want to integrate that with respect to y. Okay. These are both numbers. Let's do y equals 0 to y equals 5. And let's do x equals 0 to x equals 5. And let's do y, the square root of x plus y plus 1. And do the x's before the dy's. If they're both numbers, can't you switch them? It doesn't matter. Now that means I can use a little trick. And I'm going to call this x plus y plus 1 to the power of a half dx dy. And that is going to be a little bit easier to do because that is a constant, so that doesn't really matter. And that's just x plus y plus 1 to the half. So I should be able to just do a version of the power rule. Add 1 to the power and then divide by the new power. Are you comfortable with that integral with respect to x? Technically, there's a times 1, but I'm not writing that down because 1 doesn't do anything. I mean, if that had been 2x, wouldn't have done times a half, right? But I don't need to because it's times 1. Now, that gets me the integral from 0 to 5, 2/3 y. If you plug in 5, you get 6 plus y to 3/2. Take away, if you plug in 0, you get 2/3 y to the y plus 1 to the 3/2 dy. Okay, sort of a kind of there. I'd really treat these as two separate questions. So let's do this one. And then you can figure out how to do the other one yourself. I want to find the integral of 2/3 y, 6 plus y and 3/2. It's going to be a u sub. And it's going to be one of those u subs that might not look like it's going to work, but it is going to work. You just have to trust the math. There's not an awful lot of candidates for who the u sub should be. Who are we picking?
Six plus y.
Yeah. Just 6 plus y, nothing more complicated than that. Now, if you differentiate with respect to y, you're going to get 1. So that means du is equal to dy. That's good. So we're going to get an integral 2/3 y u to the 3/2 times du. And normally when you see an orphan left over, you should be worried because everything should be u's, agreed? So I now need to figure out what y is in terms of u. Well, if u is 6 plus y, won't y be 6 minus u? Right, that guy. And you might think, hey, all you've done is turn one ugly integral into an equally ugly integral. Not actually the case. If you multiply this by 2/3 and then by that, you get 5/2. If you multiply that by that, you get take away 4 u to the 3/2. And do you see that that is integrable, isn't it? It's just ugly powers. So I'll add 1 to the power, and then 2/7 gets me 4/24. And I'll add 1 to the power, and I believe that gets me 8/5. I like to return back to the original, which is that.
Why were the limits of integration for both the y and the x from 0 to 5? Wasn't like the y from 0 to 2 and the x from 0 to 5?
Are you saying that I've just miswrote what the limits of integration are?
Maybe, I'm not sure.
Let's check. X was 0 to 5, y is 0 to 5. Okay. Now it's right, rather than change the whole thing. Right? Okay. I should be able to now evaluate it at y equals 0 to y equals 5, or to whatever the start and finish number is. And whew, won't you do the second one the same way, but this time u plus 1 will be your, u is y plus 1, will be your limits of integration. I don't want my dogs up to now. They're like children. You're more worried when they're quiet than when they're making a noise. Because when they're quiet, those little darlings are up to something. I know they are. Okay. Are we good so far? Okay. Let's try one more. Doing a double integral, the surface integral. The guy we're going to deal with is z squared. The function that we're dealing with is that guy. And we're only told, oh, don't do that one. That is going to be a Tuesday one because we are going to be doing a change of variable on that question. And I don't want to do that method yet. So I'll just move on to 5. Okay. So this surface integral, y squared, okay, let me double check. That is also a change in variable. Next one is a change in variable. And the next one's not. Okay. Just want to stick to questions that use the method that we've been doing. So we have an x squared plus a y squared plus a z squared ds. And S is a cylinder, which is x squared plus y squared equals 16. And this cylinder is from z equals 0 to z equals 5. No, it's also a change in variable. Find one that's not a change in variable. How hard can that be? No, change in variable, change in variable, change in variable. Okay, that one was the last question we could do the way I just showed you. And so let's show you earlier than I was expecting to do. Let's show you how you do a question with a change in variable. And so I'll find my first one again where we can do that. Let's see, where are you? Now I can't find one when I want one. Okay, here we go. Question 11 is a change in variable. You're being asked to do this guy, x plus y plus z ds. You're told that S is the surface that's given in its parametric form, which is why we need a change in variable. and you're being told that u is between 0 and 5, and v is between 0 and 1. So what is going to happen to this double integral is that it's going to be changed into an integral in terms of u and v, a change in variable essentially. And everybody is going to be turned into u's and v's. And the formula for doing that is it's a double integral over d, which will be described by these two guys, of our function, x, y, and z, but now x, y, and z are going to be in terms of u and v. Times that guy, du, dv. Okay. So that's our general formula. Right. This function here is x plus y plus z. So let's turn those guys into u's and v's. So it's going to be u plus v, u take away v, and 1 plus 2u plus v. So I get u plus a u plus 2, so I believe that's 4 u's. I get a v, take away v, they cancel out. So there we go. So our double integral is going to be from u equals 0 to u equals 5, v equals 0 to v equals 1, the function in terms of u and v, times this fella. Do you recognize a cross product, and do you recognize the magnitude of a cross product? Right. So R of u is basically just that guy. What does that mean? It means you take this guy here and differentiate him with respect to u. So you'll get 1 out of that guy, you'll get 1 out of that guy, and you'll get 2 out of that guy. If you want to find this fella, you're basically differentiating that vector with respect to v. So you differentiate this with respect to v, you get 1. This with respect to v, you get -1. And this one with respect to v, you get 1. So you want to do the cross product of those two. You're going to do an I, you're going to do a j, you're going to do a k. And this one's first, so you're going to go 1, 1, 2. And this one is second, you're going to go like that. And then you're going to go so many i's, take away so many j's, plus so many k's. You cover, okay, I've got a roller today, do I? Okay. There. Major diagonal 1, take away -2. Middle one. One, take away 2. Last one. -1, take away 1. So we are going to get, I think it's 3. A negative gets you 1, and a -2. And we are interested in the magnitude of that guy, which is the square root of 3 squared plus 1 squared plus -2 squared, which is what, the square root of 14. Are you comfortable with how to do this guy here, right? Find the derivative in terms of u, cross product, the derivative in terms of v, and then find its magnitude. So I should be able to put that into the mix. So we've now got the integral from u equals 0 to u equals 5, from v equals 0 to v equals 1, 4u plus v plus 1 times this guy, which is the square root of 14, and we'll do a dv du. I would probably tidy that up just a little bit, pull out the square root of 14, we're comfortable that we could integrate that double integral. Pretty reasonable. Can you see why I wanted to avoid doing them until a new day? Because they're quite different from the first method. But it is what it is. Do we have time? Yes, we do. We'll have one last one of these, essentially changing variable stories. You normally do these when you describe the surface as a parametric equation, typically in terms of two variables called u and v. So in question 12, we have the surface integral to do. And we're told what S is. And S is going to have X is u cos v, Y is u sine v, and Z is equal to u. And we get the range of u's and the range of v's like that. Okay, let's get each piece. X, Y, Z gets turned into u cosine v, u sine of v, and a Z is just a u. So that looks like it's going to be u cubed sine v cosine v. Are we comfortable about the X, Y, Z converted into u's and v's? X, Y, Z. Now, R of u basically means differentiate these guys, X, Y, and Z, with u as your guy. So that's going to be cosine of v, that's going to be a sine of v, and that's going to be 1. You do this guy with respect to v now. If you differentiate this with respect to v, you get negative u sine v. If you differentiate this, you get positive u cosine v. If you differentiate this, you will get 0. We'll now get the cross product of those two. I have an I have a j, I have a k. That's going to be my next row. And underneath, my last row. So it's going to be so many i's, take away so many j's, plus so many k's. Okay. Nothing, take away that guy gets you negative u cosine v. Middle one, nothing, take away that guy, take away a negative gets you positive, so you'll get that guy. Last one, that guy times that guy, take away that guy times that guy, that's going to add. So I'm going to get u cos squared v plus u sine squared v. So it looks like I've got a negative u cosine v, a positive u sine v, and a u cos squared v plus a u sine squared v. And before I go any further, I've noticed that I can do something to the third term. I can simplify it. What does u cos squared plus u sine squared actually simplify down to?
U.
Just a u, right? Pull out a u's a common factor, you just get a u. Now I need to find the magnitude of that guy. So it's going to be the square root of this guy squared plus this guy squared plus that guy squared. That gets you u squared cos squared v. That guy gets you u squared sine squared v. And that guy is still u squared. Would you agree that the u squared cos squared and the u squared sine squared add together and simplify as a u squared? And so I now have a u squared plus another u squared, which gets me 2u squared. And that can simplify as the square root of 2u, as long as you assume u is positive, which we will. So I have all the pieces. We have the integral from u equals 0 to u equals 2, and the integral from v equals 0 to v equals pi upon 2. The function, which was x, y, z, is u cubed sine v cosine v. The magnitude of this guy ends up being the square root of 2u, and we're going to be doing a dv du. These guys are variables separable, which is, I think, the first one today. If you take all this stuff together and probably stick the square root of 2 outside, you get a u to the 4 du. And you have a sine v cosine v dv. That one's just 1/5 u to the 5. Any suggestions of how to integrate this fella? Sine v cosine v. How should I approach its integral?
With a u substitution?
Why not? Which one do you want to use?
I'll go with sine since we won't have to deal with negatives.
Good choice. But you could do cosine if you felt like it. It would still work. And suppose I don't want to do u subs. Nothing wrong with u sub. Do it. It's great. It works. But suppose I didn't want to do u subs. Is there another approach?
Use a trig identity.
Yep. Do you know what that one becomes as a trig identity? Because that is the way I'm thinking.
1/2 sine 2v.
Correct. And so you end up with -1/4 cosine 2v, which maybe not pretty, but you could do it. So there's lots of approaches to that one. And according to them, and I'll take their word for it, you're going to get 16 root 2 over 5. I'm pretty sure I know where the 5 comes from because it's going to come out here. I'm pretty sure I know where the root 2 comes from. Evidently, the 16 is just what the bits and pieces interacting, come to. That seems reasonable. Could well be that. Have I told you my joke about Hitler yet?
No, but I'm ready.
Are you ready? Wendell, are you ready for my joke about Hitler?
Yes, I'm ready. I haven't heard it either.
Okay then. You might not have heard it on the news, but it's just came through that they finally discovered that Hitler wasn't even Austrian. No. they found out he was Irish. And what happened is that they've discovered his original birth certificate, and he was born in Ireland. In fact, his name wasn't even Adolf Hitler. His original name was Richard Potato. But when he moved to Germany, he changed it to Dictator.
I knew it was going that direction. That was good.
You seen it coming?
Yeah.
Okay, put your names down, guys. Have a nice weekend. I'll see you Tuesday. I'll hang about for any questions. But try not to ask me a question about changing variable because they take about 20 minutes each.
On the videos things, it
Yes.
looks like for yesterday's you accidentally put your stats class video.
I didn't, did I? Okay. Thanks for telling me that, David. I'll go and fix that as soon as we finish here. So I've put my stats class in instead of yours. That was clever of me. All right. I'll go and play with that. Any other questions while I get that sorted out?
Have a
Yeah,
good weekend.
Right. Have a nice weekend.